Okay, today I'm going to continue with you the analysis of frames. I will be solving another two problems, and I'll be talking to you about stability and determinacy of frames. So the first example, I'm taking this from one of your past midterms. So we are having a frame like this. It is supported by two hinged supports, and we are having an intermediate hinge. There is a concentrated load of 10 ton and another concentrated load of 5 ton in the horizontal direction, and the rafter of the frame is subjected to a distributed load of 1 ton per meter. Assuming that this is point A, B, C, D, and E. These distances, this is 2 meters, 6 meters, 6 meters, and this distance here is 2 and 6. Again, we need to calculate the reactions, so we can take moments about point A. We can get the vertical reaction at E. It will be 7.7 ton. Summing all of the forces in the vertical direction, we should get the vertical reaction at A. It will be it will be 14.3 tons. And then we can take moments about point C from the right hand side. We include the vertical reaction and the portion of the distributed load between points C and D. We should be able to get the horizontal reaction here, and it is equal to 3.53 tons. Summing the forces in the horizontal direction, we should get the horizontal reaction here, and it is 1.47 ton. Now, let us start solving for the normal force. Again, for the normal force, we are drawing the positive normal force on the far side of the datum and the negative normal force at the near side. So here we are having, this is the positive, and here the negative, and here the positive and the negative. Remember, we are standing under the frame, so the near side will be negative and the far side will be positive. And for this column, when we are standing here and looking in this direction, so this will be the near side, which is negative, and the far side positive. Now, we want to determine the normal force in the part AB. How can we do that? Again, we are taking a section like this, and we are taking the lower portion of the frame. I am searching for the forces along the axis of the frame. Here I am having 14.3. In order for this part to be in equilibrium, I should have another 14.3 internally opposite to its direction. It means that the internal normal force is going towards or is directed towards the section, يبقى it is causing compression. This condition will persist from point A up till the cantilever. يبقى I will come here and I will draw constant normal force. Its magnitude is 14.3 compression. Because it is compression, then it is negative, يبقى it is drawn on the near side. طيب, when you are taking a section here, remember, we are not taking only the column, but you have, because if you did that, you are cutting another section here. You should be cutting only one section, which means that you are taking this part, including the 10 tons of the cantilever. يبقى if I am searching for the equilibrium of this part, I am having 10 ton downward and 14.3 upward, يبقى there should be a force here of 4.3 to be in equilibrium in the vertical direction. يبقى it means that the normal force is reduced in this portion and it became 4.3 compression because it is directed towards the section and it is uniform. يبقى in this portion I am having uniform compression and it is 4.3. طيب, if I want to get the normal force in the cantilever, I will cut a section like that and I will take the left hand side. There is no force applied along the central line of the cantilever. يبقى I don't have normal force. يبقى it means that the normal force here is 0. طيب, for the part BCD, to get the normal force, I will take a section like this. Again, I will have to take all of the left portion of the frame, including the cantilever. I will only count the forces that is parallel to the central line. I don't have except the 1.47 because the 14.3 and the 10 and the portion of the uniform load is perpendicular to the central line. The only force that is parallel to the central line is the 1.43 and it is getting outward. It means that the internal force that should balance with it should be in this direction, it is causing tension. This condition will persist throughout the member BCD. Therefore I will have here tension constant. It is 1.47 and 1.47, and we should draw the tension on the far side because this is the side where we are drawing the positive normal force. Again, for the part DE, I just have the 7.7 and of course it is causing compression. If we took a section here like this, there should be an internal force opposite to it to be in equilibrium. It means that the internal force is getting towards the section, it is causing compression. It will be drawn on the near side of the frame. This is compression here. Notice I will have to get the sign. And I will have to get, I have to write the magnitude of the normal force in the beginning and in the end. So this is 7.7 and this is 7.7. Again, if for some reason, if one of you are confused and you drew the positive normal force below the datum, or you drew the negative normal force at the far side of the frame, no problem. I will give you also the full mark. But the most important is that you tell me the sign, because when we are designing, it is very important to know whether it is tension or compression. It makes a lot of difference in the rules of design. Okay, now let us go to the shear. This is the central line of the frame. This is the shear force diagram. Again, we are drawing the shear force diagram, the positive shear on the far side and the negative shear on the near side. So we are reminding ourselves, this is the side of the positive and this is the side of the negative. We are standing under the frame, so this is the near and this is the far. We are standing under the frame, so this is the near and this is the far. And here we are standing under the frame, so this is the far and this is the near. Okay, now let us start our solution. I will start with member AB. Remember, we are standing here under the frame. As I told you, we are starting from the left hand side. So where is the left hand side? This is my left hand side. I'm starting from point A and I'm hiding all of the frame. So I'm having on this side an upward force of 1.47. It is causing positive shear. Why is it positive shear? Because it is on my left hand side and upward. I will come here and I will draw a value of 1.47. Very good. Question: what difference will it make if I'm taking a section here, or a section here, or a section here, or a section here? Nothing. Because along this edge, I don't have any variation of the loads in this direction. The 10 ton is causing compression, as we have seen for member AB. It is not causing shear. Yeah, but if you are cutting a section like this, or a section like that, or a section like that, all of the values that you are going to get is 1.47, and on your left-hand side and upward, then it is a positive shear. Yeah, therefore, this part, I will have a positive shear throughout. And it is drawn on the far side. Very good. Right. For the cantilever, I will start from the left. On my left-hand side, I am having a force of 10 ton downward. It is negative shear. Right. If I'm taking a section here, or a section here, or a section there, and only counting the left portion, I still have the 10, which is negative. On this datum, it will be drawn below the datum like this. Don't worry if you are having interference in the diagrams, that's something normal in our work. So the central or the datum is drawn in black, and the magnitude of the shear is drawn in red. Type. I want to get the magnitude of the shear at point B. What am I going to do? I'm going to take the left portion. This is the left portion. Okay? I will have to take the cantilever with me, because if you took only the column, it means that you are cutting another section, and you are not allowed to do that. Then when you are cutting a section like this and counting the forces on your left, you are having 14.3 upward causing positive shear, and 10 ton downward causing negative shear. This means at this point I am having 4.3 tons positive shear. Since it is positive, it is drawn on the far side. Type. At point D, you are cutting a section here like this and counting all of the forces on your left. What is the difference? Here I am having a distributed load with a value of 1 multiplied by 12. So we have reached positive 4.3. Because of this distributed load, the shear will drop, and it will be 4.3 minus 12, because it is on my left-hand side and downward. This value will be 7.7. How did I calculate this very fast? Because I know that the reaction is 7.7. Okay? How do I connect between this point and this point? Because the load is uniform, the shear is the integration of the load. Therefore, this part will be linear. What is the effect of the intermediate hinge in the shear diagram? Nothing, because the intermediate hinge is transferring the shear from the left-hand side to the right-hand side. The only effect for the intermediate hinge is that it makes the moment at this point is equal to 0. But the shear is compatible. The magnitude of the shear on the left is equal to the magnitude of the shear on the right. Okay. Very good. Now I want to determine the shear at point D. Why did I start from here? Because we are standing under the frame, as you recall, and this is our left-hand side. So I'm cutting a section like this. How am I going to cut a section? شوف بقى, we are cutting a section like that. We are taking everything that we have, everything. Okay? We are taking the 5. This is causing positive shear because it is on the left and upward. This is not causing shear, and also the 10 and also the 14.3. The only force that is causing shear is the 1.47. How about the shear that it is causing there? It is negative because it is on my left hand side and downward. This force is on my left hand side and downward. So I'm having positive 5, negative 1.47, so it is positive 3.53. How did I calculate this very fast? Because I know that the reaction is 3.53. It should be equal to the reaction. Here I'm having positive, and it is 3.53. Type. If you are taking a section here, or a section here, or a section here, there is no difference. It is the same. Therefore, I will have here a constant value, and then we will face the 3.53. It is pointing downward, so it will get us back to 0. Therefore, here, this will be the magnitude of the shear diagram. Okay? Very good. Now we want to draw the big guy, the normal force diagram, the most important diagram ever is the bending moment diagram. For the bending moment diagram, we are reversing. The near side is the positive and the far side is the negative. Here, the near side is the positive and the far side is the negative, and here, negative and positive. Let us start now for the normal force, for the bending moment diagram. I will have to erase this, please, because I need this part while I'm explaining. Very good. Okay. The magnitude of the bending moment at point A is equal to 0. Because when you are cutting a section here, all of the forces are passing through point A, so I don't have bending moment. This point where the cantilever meets with the column of the frame, this point here, basically it is 3 points. I would advise that you have to draw for me the free body diagram of that point. If I will have to draw this intersection like that. Let me ask you a question. The moment here and the moment here and the moment here, how do they relate? They should be in equilibrium. If I should get the moment at this section, how much is that? It is the 1.47 multiplied by its distance, which is 6. And it is rotating in this direction. Okay? So I'm having a moment here, which is 6 multiplied by 1.47. Okay? Type. What is the moment here in the cantilever? I will take the cantilever portion only. So it is the 10 multiplied by the 2, and it is rotating in this direction. So I am having here the 2 multiplied by the 10. How can this moment be in, or how can this joint be in equilibrium? This is 20. And if you calculated that, this will be 8.82. Therefore, this is bigger. Therefore, I should have the moment in this direction to be in equilibrium. And its value is 20 minus 8.82. So it will be 11.18. Now let us draw this here. For the 8.82, it will be drawn. We always draw the bending moment on the side of the tail of the arrow. So it will be on the right hand side. Like this. The bending moment here is 0. Because the shear is constant, the bending moment will have to be linear. Top question. What is the sign of this part? Because it is drawn on the near side, it is positive. And its value is 8.82. Very good. Top, the bending moment at the end of the cantilever is 0 because the forces are all passing there. So I'm having here 0. What is the bending moment at the end of the cantilever when it meets with the column? It is negative 20 because the tail of the arrow is above the datum. So we are drawing the bending moment on the side of the tail of the arrow. So here it will be 20. How do I connect? I am having constant shear, therefore the bending moment is linear. Now the bending moment is drawn above the datum, therefore it is negative. Okay? Now I want to draw the 11.18. Where is the tail of the arrow? We decided on the direction of the 11.18 from the equilibrium of this joint. But now when I draw it on the diagram, it will have to be drawn on the side of the tail of the arrow. So I will come here and I will plot 11.18. Very good. طيب, this point B, again, it is 2 points. It is not 1 point. This is point B. Now I need to calculate the moment here, and the moment here should be in equilibrium with it. How do I calculate the moment here? I will take 1.47 times its distance, which is 8, and it is rotating in this direction. And I will take the 10 times its distance, which is 2, and it is rotating in this direction, right? يبقى therefore I am having, this is causing negative moment and this is causing positive moment, okay? So it is 10 multiplied by 2 minus 1.47 multiplied by 8. This will give us the magnitude of the moment here is 8.24. Again, how did I get this? This direction I am having, or this force is rotating in this direction like this, which is 10 multiplied by 2. And the 1.47 is rotating in the opposite direction, like that. So it is 1.47 multiplied by 8. يبقى this is minus 1.47 multiplied by 8. Because this is the bigger amount, يبقى I am having the resultant moment at this section is 8.24. How can this joint be in equilibrium? There should be another moment opposite to it in direction and equal to in magnitude, which is 8.24. In the diagram, where am I going to draw this bending moment? On the side of the tail of the arrow. So simple. The tail of the arrow is on the left, so it will be drawn on the left of the column. And the tail of the arrow is above the beam, therefore it will be drawn above the beam. If I will come here, and this will be value 8.24, and here this value is 8.24. Type, we have reached a value of 11.18. I will have to connect this like that, and this will be negative as well. يبقى this will be the bending moment diagram on the column. Take care. What is the relation between this line and this line? They are parallel. Why are they parallel? Because I am having the same magnitude for the shear, and the shear is considered to be the slope of the bending moment. Okay? طيب, the bending moment in this part is very easy. What is the bending moment at point C? The bending moment at point C is equal to 0 because this is an intermediate hinge. So again, I will be using the method of superposition. We know the magnitude of the moment here 8.24, and we know the moment here is equal to 0. I am having a distributed load in between, so I'm going to connect this like that, and I'm going to suspend a parabola. What is the magnitude of the parabola? It is 1 multiplied by 12 square over 8. Okay? When you draw this, it will be something like this. You will notice that the maximum bending moment will be corresponding to the point of zero shear. Okay? Type at point D. Again, point D. Let me erase that. Okay, we will take the equilibrium of joint D. Now, joint D is basically composed of 2 points. It is easier to get the bending moment at this section from the lower portion of the frame. You just have 3.53 multiplied by 8, so it will cause moment in this direction. So we are having moment here, 3.53 multiplied by 8, which is 28.24. How can this joint be in equilibrium? There should be a moment in the opposite direction, and it has the same value, 28.24. Now we got the moments at point D. Let us draw this there. So I'm having here, the moment will be drawn above the datum, because the tail of the arrow is above the datum. Its value is 28.24. Again, the moment here is 0, and the moment at point D is equal to 0, is equal to negative 28.24. So in between, I am having a distributed load. Therefore, I will connect between these 2 points and will suspend a parabola. The magnitude of the parabola is equal to 1 multiplied by 12 square over 8. How did I know that this value will not be below the datum? From the calculation. Here this is 28.24, so half this value is 14.12. Of course, 12 square over 8 is something less than 14.12, it's about 9. Therefore, we get the value, or the parabola here will be drawn as such. And this is negative because it is drawn above the datum. Type. The other moment, which is 28.24, the tail of the arrow is on the far side. So this means that I'm going to draw the bending moment 28.24. And the magnitude of the moment at point E is equal to 0. So this value is equal to 0. In between point D and E, I don't have any loads. The shear is constant, therefore the moment is linear. This is the final shape of the bending moment diagram. What does this diagram tell us? If you want to plot the cracked side and investigate the shape of reinforcement here. Now, this frame is something like this. From the bending moment diagram, we are having here this side is having tension because the bending moment is drawn on the tension side. For the cantilever, the upper part is under tension, and for the upper portion of the column, the tension side is on the left. For this part, we are having part of this beam is subject to tension at the upper fiber, and the other part is subject to tension at the lower fiber. So if I want to locate the reinforcement will be like this to close the cracks. The reinforcement in the cantilever will be like that to close the cracks, and here the reinforcement will be like this to close the cracks. And this part, we are having the tension at the lower fibers or at the bottom fibers, so we should have bottom reinforcement here. Type. In the other portion, we are having the moment, all of the moment here is negative. It means that the cracks is at the outer face or the far face. So this means that the reinforcement should be located this way at the outer fibers to close the cracks. It is very important to draw the bending moment correctly so that we can know the distribution of reinforcement in this frame if it is made of reinforced concrete. Now let me solve another problem with you. Another example. This problem also will be taken from a previous midterm exam. We are having a frame like this. It's hinged support and hinged support, and we are having here distributed load. And we are having an intermediate hinge here, and we are having a concentrated force in this direction, 2 tons and 2 tons. these distances are given to us. It is 2 meters and 4 meters, and these distances, it is 1 meter, 4, 4, and 1. Now, if we call this point A, B, C, D, and E. Now we notice something. You can work traditionally, but you can discover that the structure itself is symmetric, because the geometry on the left hand side is the same as the geometry on the right hand side. The type of support that we have is identical to the type of support that we have here. This is not only enough, the loads are also symmetric. So we are having this portion is subjected to a uniform load of 2 tons per meter run, and there is a concentrated load applied at this point. The same thing on the other side. You will notice that some of the diagrams will be symmetric, similar to the frame, and other diagrams will be skew symmetric. Let us see this. First, we will get the reactions. If you took moments about point A, you should be able to get the vertical reaction at E, and this should be equal to 10. Of course, it goes without saying, because the problem is symmetric, the reactions are also symmetric. So this means that the total sum of loads is 2 multiplied by 10, which is 20. This reaction is 10, and this reaction is 10 as well. And of course, here we should have this reaction is 2, and this reaction is 2, from sigma fx is equal to 0. Now we are going to draw the normal force diagram. Let me go faster a little bit this time. Okay, this is the normal force diagram. We are having here again far face positive and near face negative. Type. If I want to get the normal force at this section, I will take the lower portion. I'm having 10 tons, so it is causing compression. The condition persists throughout the member AB, so I am having here, this is normal force, compression, and it is equal to 10 and 10. In this portion, if you take a section like that, and you took the left-hand side, there is no forces applied along the central line. All of the forces are causing shear and bending moment. This part I am having 0 normal force. Okay? And I'm sorry. There is something wrong here. If you want to get the reaction, you should take the moments about point C from the right hand side, or the moments about point C from the left hand side, and the reaction here will be 1.83 ton, and this is 1.83 ton. Okay? So if I want to get the normal force in the part BCD, I will take a section like that, and I will take the left hand side. So I'm having 2 and 1.83, they are both causing compression. So the resultant here is compression, and it is equal to 3.83. Now I'm having here normal force compression as well, which is 10 ton like that. One student can make use of the symmetry of the structure, and you just indicate this for me, that it is symmetric. You don't need to draw the right hand side of the normal force. If you indicate this for me, it means that as long as this part is subject to compression 3.83, this part as well will have the same value. If this is 0, this will be 0. If I'm having normal force here 10 compression, I will have here also normal force 10 compression. So you can draw the normal force diagram as such. طيب. For the shear, طيب, how we are going to start? As usual, we are starting from the left hand side. So I will start here. On my left hand side, I will take the force 1.83. It is on my left hand side and downward, therefore it is negative shear. Remember, this is the near side, negative, and the far side is positive. Like that. Again, I will start from point A. I will be hiding all of the frame. I am having 1.83 on my left hand side and downward. Therefore it is negative and it is 1.83. This condition will be the same between point A and the concentrated load up till this point here. And then starting from this point and above, when you are taking a section like that, you have to count the forces on your left. So the forces on your left is the 1.83 and the 2, they are both on the left hand side and downward, therefore it is 3.83. And this will be constant like that. Okay. Now let us take the beginning of the cantilever. Again, I am taking a section here. I am not taking any forces, so the shear at this point is equal to 0. Up till we reach this point, we take the left portion of the beam. It is 2 multiplied by 1, it is negative 2. So it is on my left hand side and downward, then it is negative like that. Between this point and this point, I'm having constant load, therefore the shear must be linear. Okay, we are having a sudden change in the shear due to the 10 ton. We have reached at this section a shear of negative 2 and we are having positive 10 because it is on my left hand side and upward, we are having positive 8. Okay? Between this point and this point, we are having distributed load. Its magnitude is 2 by 4 and it is downward, then it is negative 8. So it will reach here 0. You will notice that the shear diagram is skew symmetric. What does this mean? Skew symmetric can be indicated like this. See? I'm drawing 2 flags, but they are not as the symmetric. This is symmetric. The flag is on the same side, but this one is skew symmetric. What does this mean? It means that when you complete the shear diagram, it will be like this, and it will be like that. This is 2, and this is 8, and here we are having positive 1.83 and 1.83, and here this is 3.83 and 3.83. So this is positive, positive, negative, and positive. So you can either draw the left hand side only, as we said, and you are drawing the indication of skew symmetric diagram. Always the shear is skew symmetry, skew symmetric. طيب, for the bending moment, the bending moment diagram. Again, it is opposite in the sign convention. The far is negative and the near is positive. The far is negative and the near is positive. Okay, we will start the bending moment at point A. The bending moment here is equal to 0. All of the forces are passing through the point. It is not a fixed support. So we are having the bending moment here is equal to 0. The bending moment at this section, the only force that is causing the bending moment is 1.83, and it is rotating in this direction. So the tail of the arrow is at the far side, and the magnitude of the moment is 1.83 multiplied by 4. So if you did that, this will be 7.33. Between this point and this point, the shear is constant, therefore the moment is linear. Since the moment is drawn on this side, therefore on the far side, therefore it is negative. Type. We are having point B. Again, point B, we are having 3 sections. We have to draw. My advice is that you have to indicate for us the free body diagram for each intersection. So here we are having this point is basically, or point B is basically 3 sections. The section from below, I will take 1.83 times its distance, which is 6, and the 2 multiplied by its distance, which is 2. Therefore we get bending moment in this direction like that, and its value will be 14.98. The section left of point B, I'm taking only the distributed load. So the resultant of the distributed load is 2 multiplied by 1, and the distance here is 0.5, so it is 1 meter ton. How can this joint be in equilibrium? These 2 forces or these 2 moments are rotating in the counterclockwise direction. Therefore, I should have this moment to balance with them, and it is 15.98. Okay, let us draw this. The 14.98 is drawn on the column. So here, the magnitude of the 14.98. How do I connect between the 14.98 and the 7? By a straight line. Like that. And of course it is negative because it is above the datum. Type the 1 meter ton, the tail of the arrow is above the datum, so it will be drawn here. This is the 1. The bending moment at this point is equal to 0. I want to connect them. Don't forget that we are having a distributed load. So I'm going to connect these 2 like that and then suspend a parabola. What is the magnitude of the parabola? It is 1 square multiplied by 2 over 8, which is 0.25. All of the parabola, all of the bending moment will be a negative moment as such. Type. The bending moment at point C is equal to 0, and the bending moment right of point B is negative 15.98 because the tail of the arrow is above the datum. We are having the bending moment here is 15.98. Now I want to connect these 2, but we are having a distributed load, so I'm going to connect these 2 like this. This value is almost 8, but I want to go down a value of 2 multiplied by 4 square over 8, which is how much? This is 16 over 8, then this is 4. This value is half of the 15.98, which is almost 8, and the magnitude of the parabola is the distributed load times the span square over 8, which is 4. يبقى it means that the parabola will be like this. There is no part of the parabola that will go below the datum. Okay? Again, you will notice that the bending moment, similar to the normal force, is symmetric. Which means that if you try to draw the other side, it will be like this. This is 1, and this is 15.98. And here we are having 14.98, and here 7.33, and this part is negative, and this part is negative. Okay? So the bending moment is symmetric, and the shear force is Q-symmetric. This is symmetric, because the loads and the geometry, they are both symmetric, and the shear will be skew-symmetric. According to this bending moment, if you would like to find out how we are going to reinforce this frame, so simple. Okay? Now the bending moment is drawn on the left. يبقى this means the tension side is on the left. يبقى I am having cracks like this. The bending moment all throughout is above the datum. يبقى therefore this means that the tension cracks will be above the datum. يبقى when I'm putting the steel reinforcement, the steel reinforcement will be located at the upper fibers, and the steel reinforcement will be located left of the column, like that. And of course this is symmetric as long as the bending moment is symmetric. Okay? So we solved so far up till this moment, we solved 4 problems of frames, 2 problems on each lecture. Your exams and your assignments will not be more difficult than this. Now let me explain for you one last point in the frames, and to conclude this chapter. I am going to talk about stability and determinacy of frames. We all know stability. But I'm going to focus here on determinacy of frames. Take care. Now, if I am having a frame like this, this is a frame, okay? How many support reactions do I have? I am having here 1, 2, and 3 support reactions. So I'm having R1 and R2 and R3. يبقى how many reactions? We are having 3 reactions. How many equilibrium equations? We are having 3 equilibrium equations. We don't have intermediate hinge. يبقى the condition equation is equal to 0. This means that the total number of unknowns, which is the reaction, is equal to the total number of equations that we have, the equilibrium and the condition equation. يبقى therefore this is R is equal to E plus C. يبقى therefore it is statically determinate. What is the meaning of statically determinate? It means that you don't need except the equilibrium equation and the condition equation to solve for the external support reactions. Very good. Now if I ask you to draw the normal force diagram and the shear force diagram and the bending moment diagram, what are you supposed to do? You are going to cut a section like this and either take the left hand side or the right hand side. We have already solved for the reactions, right? Using the external equilibrium and the condition equation. Very good. When you are cutting a section like that, you are not cutting except through one section. So if you took the free body diagram of the left hand side, it will be something like this. This is R1 and this is R2. You will find that this part is not in equilibrium. Imagine that you are having any kind of forces. Okay? Any kind of forces here. When you take this portion of the structure, it will not be in equilibrium. Therefore, there should be an internal force at the cut section to make this portion in equilibrium, since it is already taken or driven from a structure that was in equilibrium. We are going to have normal force because it is along the axis of the member, and shear force perpendicular to the member, and bending moment. These are the three internal forces. Top question, how can you solve them? You are going to say sigma fx is equal to 0. You are going to get the normal force. And sigma fy is equal to 0. You are going to get the shear. And sigma the moment about any point is equal to 0. You will get the bending moment. So I am going to use the three equilibrium equations after taking the cross section or after taking your section to determine the three internal forces. Therefore, this structure is externally statically determinate because I can use the equilibrium and the condition equation to solve for the support reactions. And also it is internally statically determinate because I can, whenever I am cutting a section, I'm going to get only three unknowns and I'm having three equilibrium equation. Therefore, this structure is externally determinate, and also it is internally determinate. Why is it externally determinate? Because we can take the overall equilibrium and we can solve for the support reactions without need to any other equation except the equilibrium and the condition equation. Why is it internally determinate? Because whenever you are cutting a section, you will get only three unknowns and you are having three equilibrium equations. Therefore, it is internally determinate as well. How about if the structure is like that? Okay. Now again, if we are having any kind of forces here applied like this, and you are going to solve for the support reactions. Tell me how you are going to solve for the support reactions. You will take moments here and you will be able to get R2 and sigma Fy is equal to 0. You are going to get R1. Sigma Fx you are going to get R3. Therefore this structure is externally statically determinate. So it is externally statically Why? Because we are having the number of reactions is equal to the equilibrium equation plus the condition equations. طيب, let us try to draw the bending moment or the shear. What are you going to do? If I want to get the shear and the normal force and the bending moment at this section, I cannot take a section like this. This is not a correct section. because still the structure is connected. You have to cut this way. يبقى in this case, when you are cutting this way, you will be getting how many internal forces بقى? This is R3 and this is R1. You are cutting a section here and you are cutting a section there. So you are getting normal force N1, shear Q1 and bending moment M1, and normal force N2 and shear Q2 and bending moment M2. Okay, now when we took a section like that, this section is passing through two cut sections. Each cut section is giving us 3 internal forces. طب how many equilibrium equations do we have for this part? We are having only 3 equilibrium equations. يبقى we are having 3 equations and we are having 6 unknown forces. يبقى therefore we are having 3 extra unknown forces. يبقى any closed frame like this will be 3 times internally indeterminate. يبقى therefore this frame is externally determinate because we were able to determine the support reactions using the equilibrium equation. But whenever we want to draw the normal force and the shear force and the bending moment, we will not be able to do that. Because when you are cutting a section, this section will have to separate the frame into 2 separate parts completely. You will get 6 unknowns. And all what you have is 3 equilibrium equations. يبقى therefore this frame is 3 times internally indeterminate. Now, before I solve several problems for you to clarify this concept, take care. Whenever you are having a closed frame like this, then automatically I am having three extra unknowns. It is 3 times internally indeterminate. Now, if the frame is opened like that, there is no problem, because when you are taking a section, you can pass through one section only, which will have 3 unknowns, and you are having 3 equilibrium equations. If you want to get the normal and the shear here, you will cut like that. There is no problem. You will only get 3 unknowns. If you want to get the normal and the shear here, you will cut like this. There is no problem because you will have 3 unknowns and you are having 3 equilibrium equations. Now, let us see if we understand what I explained. I will be giving you several problems to investigate together. It is required here in all of these problems to check stability and determinacy. So example 1. Now I am having a frame like that. Very good. Let us see. How many support reactions do I have? I am having 1, 2, because this is a hinged support, 3, 4, and 5, because this is a fixed support. So first of all, stability. Let me ask you a question. Do we have parallel reactions? No, because reaction number 1 is not parallel to reaction number 2. All of the reactions need to be parallel so that we can say that this frame is unstable. Because reaction number 1 and reaction number 2, they cannot be parallel, therefore the reactions are not parallel. Do we have concurrent reactions? No, because this reaction does not meet with that reaction. They are always parallel to each other. We don't have concurrent reactions. To be unstable due to concurrent reactions, all of the reactions should be passing through the same point. Type, do we have unstable geometry? Of course we don't have unstable geometry, because if you applied any force, the structure will undergo deformation, and when you remove this force, it will come back to its original configuration. طيب for the determinacy we learned we have to study the external determinacy first. How many reactions do I have? I am having 5 reactions. How many equilibrium equations? I am having 3 equilibrium equations. How many condition equations? One of the students will tell me, well, I need to count this one condition equation for the external determinacy of the structure. I will tell him or her, no please. Because in order to benefit from this intermediate hinge, how are you going to cut through it? You cannot cut like this. Because now, still the structure is connected in this part. You will have to cut like that. As long as we are cutting a section through the intermediate hinge and there appears internal forces, let us keep this hinge for the internal determinacy. Okay? Therefore, for the external determinacy, as if this hinge is not there. Okay? I'm not going to benefit from this hinge to get the external support reactions. So I will say here, the condition equation is equal to 0. Therefore, we are having R is bigger than E plus C. Therefore, it is 2 times indeterminate. Externally indeterminate. But how about internal? Now, this is not a closed frame because it is open. There is no member here. But this one is a closed frame. What did we learn in the previous problem? Whenever you are having a closed frame composed of 4 members like that, or it is a closed loop like this, it will give you 3 extra unknowns. Because when you are cutting a section like that, passing through the frame, you will have to be cutting through 2 sections. Each section is giving you 3 unknowns, so you are having in total 6 unknowns. And you are having 3 equilibrium equations, therefore I'm having 3 extra unknowns. But don't forget, you are having an intermediate hinge. Okay, the intermediate hinge is giving me how many condition equations? The number of condition equations is equal to the number of connected members minus 1. How many members are connected? We are having 2 members are connected. Therefore, this is 2 minus 1, it is 1. Therefore, this part or this structure will be 2 times internally indeterminate. We are having 3 extra unknowns, but we are having 1 condition equation provided by the intermediate hinge, so 3 minus 1 will be equal to 2. So this frame is 2 times internally indeterminate. So in total, if I want to solve this frame, I will find that I'm having 2 extra external supports. And if I want to draw the bending moment and normal force and shear, the internal forces, I will have 2 extra internal forces. So in total, this frame is 4 times statically indeterminate. I need to get something different than the equilibrium equations and the condition equation to be able to solve for the support reactions and the internal forces. The configuration of this frame we have in front, it is stable. It is stable and it is 2 times externally indeterminate and 2 times internally indeterminate. Okay? Let's have another example. Example 2 and example 3. Let us expedite a little bit our work. Now, if you are having a frame like that, How many support reactions? We are having 1, 2, 3, and 4. First of all, definitely it is stable because the reactions are not parallel. 1 is not parallel to 2. The reactions are not concurrent because 2 and 3 and 4 are parallel. They will not meet at a point. If we applied any fictitious force in the lateral direction, the structure will undergo deformation and will come back. So this means that it has a stable geometry. The total number of unknown support reactions is more than or equal to the equilibrium equations. يبقى therefore this is a stable structure. طيب externally, the support reactions is 4. The equilibrium equations is 3. I don't have any condition equation, is 0. يبقى therefore the degree of indeterminacy is R minus E plus C, therefore it is 1. يبقى therefore it is once externally indeterminate. طيب internally بقى, this is not a closed frame. Okay, there is no problem. I can take a section here like this and solve for this part to determine the internal forces in this section. Also the same thing here and the same thing there. I can take a section like this and I can take a section like that. Okay, so I can draw the normal force and the shear force and the bending moment for this lower portion. But whenever you are getting this closed frame, you cannot do that, because how are you going to cut a section? You are going to cut a section like this. You are cutting 2 sections, 6 unknowns, and you are having 3 equilibrium equations. Or you are cutting a section like that, 6 unknowns. Or you are cutting a section like this, 6 unknowns. Therefore this closed frame is giving me always 3 extra internal forces. The same thing, I'm having another closed loop. Therefore internally, we are having the degree of indeterminacy is 6. It is 6 times internally indeterminate. In total, this structure is stable. It is once statically indeterminate and 6 times internally indeterminate. Type, what if I did that? I will come here, the same structure, but now we introduced an intermediate hinge here, like this. Type, stability, it is definitely stable because we are having 4 reactions and the number of equilibrium equations is 3. Therefore we are having definitely a stable structure. Therefore this is stable. Type external, now we are having here the number of reactions is equal to 4, the number of equilibrium equations is equal to 3, and the condition equations. Let us save this member because whenever you are cutting, you have to be cutting through one of the other members, so the internal forces will appear. Therefore let us say that the condition equation here is equal to 1. Therefore this is once externally indeterminate. Okay, type internally. Take care. Here I don't have a closed loop, there is no problem, and the same thing here, but this one is a closed loop, it gives me 3 and gives 1, and this one is giving me extra 3 unknowns. But how many condition equations do I get from this intermediate hinge? How many connected members? 1, 2, 3, and 4. Therefore we are having 4 connected members minus 1, we are having 3. This time the degree of indeterminacy will be 3 plus plus 3 minus 3. This is 3 plus 3 minus 3. So it is 3 times internally indeterminate. Okay? يبقى finally this frame, if I want to classify it, it is stable. It is externally once externally indeterminate and 3 times internally indeterminate. Okay? Another example. If we are having something like this, take care, something like that. This is example 4. With respect to stability, definitely this will be stable. How many reactions? We are having 7 reactions. So stability, it is stable already. Reactions are not parallel, reactions are not concurrent. I am having stable geometry. The total number of reactions is exceeding the total number of equilibrium equations and condition equations. Therefore, this is stable. There is no problem about that. For the external indeterminacy, the number of reactions is equal to 7. The number of equilibrium equations is equal to 3. Can I use this intermediate hinge to determine one of the support reactions? Imagine with me how you can use it. Now, you cannot cut like that, but you can cut like this. شوف, you are cutting like that, so that you can separate the structure into 2 separate parts. You are taking the link member and you are taking this portion. It means that you are cutting here. As long as you are cutting here, let us keep the intermediate hinge to count the internal indeterminacy. I cannot benefit from this intermediate hinge to calculate the reactions, because when I'm cutting a section, I will get extra internal forces I cannot solve with the support reactions. Therefore, I will count here. The condition equation is equal to 0. Therefore, the degree of indeterminacy is 4. It is 4 times externally indeterminate. Type internal. Now, this is not a closed loop, because here we don't have a member here. If you are cutting a section like that, you can take the left-hand side and you can solve. The only unknown that will appear is at the cut section. And the same thing here. And the same thing for this lower portion of the column, and the same thing for the lower portion of the column. But if you are cutting a section like this, then you are passing through 2 sections and you are having totally 6 unknowns. This is one closed loop. It will give us 3 extra internal forces. But how many intermediate hinges do I have? I am having here an intermediate hinge and an intermediate hinge. This one is giving me how many condition equation? I'm having 2 connected members only. This is one member, because the hinge is not found in the member as in the previous example. We are having one member connected to another member here. So the number of condition equations is equal to 1. And here we are having one member, because the intermediate hinge is not found in the center or is not cutting the vertical member. The vertical member is one piece like that. And therefore I'm having here 2 connected members, and we are having an intermediate hinge here. So we are having the condition equation is equal to 1. So internally we are having the degree of indeterminacy. It is 3 minus 1 minus 1. Therefore it is equal to 1. Therefore it is once internally indeterminate. Okay, then according to this, according to these two lectures that we took together, you should be able to solve the bending moment, normal force, and shear force diagram of frames. We solved together 4 examples, and we solved also 4 examples on stability and determinacy of frames. You should be able to classify whether this frame is stable or not, and if it is stable, then what is the classification with respect to external determinacy and the internal determinacy, as we explained together. This will be the topic of assignment number 4. You should be able to submit this assignment, as we said, next Thursday, okay? The 6th of April. Thank you.